Hey everyone, welcome to the last day of TrinMathCamp. As usual, we'll give everyone a few minutes to get in, and then we'll start with the usual polls, go over some homework, and the last topic is game theory.
Akash, if you could promote Michael to panelist. Yeah, so we'll be getting started in a couple minutes. We're talking about, in this lecture, we're talking about combinatorial game theory today. So really an interesting branch of mathematics that's really, I don't say, I don't know if it's really, I don't think it's really taught in most schools. So I think it'll be definitely a really great thing to be learning today. And definitely tune into our second lecture if you're still interested in game theory. It'll definitely, from 3 to 5, we'll definitely be talking about different things. We'll be talking about like kind of like more traditional game theory, and think like prisoner's dilemma and like how do you evaluate game matrices and stuff like that. I think like it doesn't matter what grade you're in. I think both are definitely really, really interesting things to learn about. Definitely if you haven't learned about them before, uh, because it seems accessible to a variety of ages, and it's definitely really, really interesting stuff that most people don't have access to until they're in college. Okay, yeah. Akash, do you want to get started with the polls intros?
Yeah. All right. So as usual, we have some polls to start off the day. So there's definitely some Marvel-inspired questions. We got a suggestion to do that, and then some great responses about Marvel. So we definitely tried to incorporate that.
Akash, can you enable screen sharing?
Yeah. All right, you should be good.
So Akash, you can just see the presentation, right?
Yeah. All right, as expected, Marvel is completely dominating DC. Although, if you take out when they're trying to copy Marvel, they've had some good stuff. So you're talking about yesterday, Wonder Woman was pretty good. The Dark Knight trilogy obviously was great.
I'm really excited to see what's the favorite MCU movie. I don't know.
Favorite MCU movie? It's okay. So the Endgame seems to be coming out on top.
I don't know, man. I don't know. I liked Captain America: Civil War a lot.
Yeah, thank you. Michael was not on the same page there yesterday.
Or even Winter. Yeah, no. I think I like Civil more than Winter Soldier.
Civil War is probably just more enjoyable because it's just on a bigger scale.
Yeah.
Although Winter Soldier, Civil War is basically almost an Avengers type of movie. So if you think about standalone type of movies, Winter Soldier is definitely up there.
Yeah.
Okay, someone had a comment about the Dark Knight trilogy. It's because Christopher Nolan directed it. Yeah, he's pretty good.
Favorite MCU character?
Someone's saying they can't see the poll results. Yeah, so just to clarify, people are still voting right now. People are almost done, sir, at around 80%. But as soon as most people are finished, then we'll release results so everyone can see what people think.
Favorite MCU character? That's also very
It's It seems to be a battle between Iron Man and Spider-Man.
I think we kind of thought like Iron Man was going to win yesterday.
Yeah.
So
Actually, Spider-Man, believe it or not, is in the lead right now. Oh, and just to clarify, when it says, which day of TrinMathCamp was your favorite? So for you, some of these might not sound familiar because they're from our 3 p.m. session. So for every day, we had 2 sessions. So don't worry about if you don't recognize some of the other sessions. By the way, if you are curious about any of them, they're all on our YouTube. So feel free to check them out even if you didn't go.
please subscribe.
All right, so we'll close the poll in a little less than 30 seconds. So try to get in your last votes. All right, so I'll end the poll now, and I'll just share the results. So as expected, Marvel completely beat DC at a 91% versus 9%.
Endgame.
Yeah, you know, they just can't make a movie. I was talking to about this with Foyez, Michael, and our other co-captain Maia last night, and DC, I just don't know what they do. I used to think that just all superhero movies were just good, and then I watched like Man of Steel or Justice League or something, and it's
I don't know. I have hope. With
hope.
Wonder Woman, they're doing some good
Wonder
stuff.
Woman's good. Yeah, that's true.
Oh wait, I'm actually confused. What is Deadpool Sony?
No, Deadpool's Marvel. I mean, he's not in the MCU, but he's Marvel.
Is he not in an MCU because of Sony?
He's not in the MC. I think maybe something. Oh yeah, sorry. It's in the chat now. A fellow Trinity student, Ferris, is telling us that it's because of Fox. Yeah, I remember this now. Fox. They had this whole deal with Fox, and I think they owned Deadpool and like X-Men and Fantastic Four or something like that. And then Disney recently acquired those characters back. So I think there were a few months ago, there was a lot of talk about how to bring the Fantastic Four and perhaps the X-Men into the MCU.
And some people are bringing up good points that the DC shows are indeed very good, like Arrow, Flash.
Right, that's actually true. That's true. I recently stopped watching it, but the first season of The Flash I thought was really, really good.
Is that the one with what's his name? The Doc Wells?
Yeah.
I just
that was
started.
really good.
As soon as school finished, I just started.
Favorite MCU movie? Okay, so Endgame won, which is somewhat understandable.
I guess.
Yeah. It was really
sorry, what did you say?
It's like one of the longest movies I've watched.
Yeah.
Surprised the other ones aren't higher.
Like what?
Look at any of them, frankly. I don't know. I feel like if I was doing the poll, I would have just selected all of them.
Yeah, these are definitely all good. I guess I could put some of them into like tiers in a way. It's hard to rank all of them.
That's true. Yeah.
I almost feel like the Avengers movies kind of have to be in a category of their own, and then you should probably just compare the standalone movies. Endgame is just so much bigger than say Spider-Man or something. See, grade, we have a lot of 8th graders, some 9th and 10th.
Very surprising
Some-
that for 9 to 12 section. Oh, I guess it is the 8 to 12 section. I was expecting more people in high school.
Some ambitious 7th graders, so shout out for the challenge.
And a few 3rd graders. Very.
Yeah, definitely. What day? Combinatorics and competition seems to be the winner here.
I like that session too. I think it was good.
Yeah.
Maybe today we'll change our mind.
Yeah, I mean, we have 30% of people anticipating that today will be an amazing day. So we don't think you're wrong.
Yeah.
Let's see, what else? Favorite MCU character? Spider-Man 1.
Oh.
Tony Stark and Iron Man. I feel like that's good. Captain America. I don't know. I mean, I like the Captain America Civil War movies and Winter Soldier.
I think the movies are good. Michael was not a fan of his character. I guess
Yeah.
if you're just doing character, maybe not, but his movies are great.
Sure.
Someone's saying, what's the MCU? It's the Marvel Cinematic Universe. So basically just all those Marvel movies. I don't know. Spider-Man just has life and history outside of the MCU, which is probably why. Yeah. Anyway, well, interesting results. By the way, just for people who are asking in the chat about our opinions, favorite MCU character, I would go with Tony Stark. And let's see, favorite MCU movie?
I'll go with Infinity War. Basic, but I gotta go with Infinity War.
Yeah, so it's between Infinity War and Endgame for me. I think, like, in an intellectual way, Infinity War is better. I think in terms of, like, you know, director type of stuff, I think it's more impressive what they managed to pull off. But just as a fan of the MCU and appreciating all the characters, Endgame is just, I think, such a perfect end to a decade-long arc. We should have done catchphrase. I was actually thinking about that yesterday. I was thinking I was going to put I am Iron Man, I am inevitable, and just a ton of other quotes. I completely forgot about that. That's rough. I should have done that.
I know the Marvel movies do not have the same directors, but I believe the Russo brothers directed quite a few of them.
Yeah, the Russo brothers are great. They did Winter Soldier, Civil War, Infinity War, and Endgame. So they did a lot of the good ones. They were really good at just managing so many characters. Anyway, I guess this is TrinMathCamp, not TrinMCU camp. So maybe let's try to get to some game theory here. All right, I'll stop sharing and then I'll let Foyez get to it.
Akash, do we want to go over 1 or 2 homework problems from yesterday?
Yeah, sure.
Let's do 1 or 2,
Just
yeah.
give me a minute to pull that up. If you have any spiel about game theory you want to say, then go ahead. It'll take me just a minute to pull up the complex number stock.
Yeah, I mean, I think game theory is, for me, it's my favorite field of mathematics. So I basically took a 1-year course on it this past year with Maia was also in that course with me, and it was definitely really interesting. Definitely after this year, it definitely changed to my favorite field. It's very applicable to many things, and it's very interesting just because you can play games, to start the class and understand it, and then you can actually dive into some nice mathematics. So I think it's really fun. But yeah, I think you guys will learn some really nice things today.
All right. So I think I have it up. I'm just going to share my screen. All right. So hopefully you guys see the complex number problem right now.
Yeah, let's do this one, Akash.
All right, cool. So I'll just read it out and then we can talk about how to do it. So there's a complex number z with imaginary part 164 and a positive integer n such that z over z plus n equals 4i. And the goal is to find n. So first we can let z equal a plus 164i. So if we remember, the real part and imaginary part, just taking out the annotation. So we see that imaginary part 64. So that's why we put this 164 here. And then a denotes the real part, which we don't quite know what it is yet. So then this is just by substitution. So we take this z plus z over z plus n. So this is z, and then this is z plus n, and then it equals 4i just by the given equation. And then over here, we just multiply both sides by z plus n. So we're just left with the numerator here, a plus 164i. And then this is the 4i we already had, and this is our denominator, a plus n plus 164i. And we just put the n to the left. We just moved it over just because, as Foyez mentioned yesterday, it's oftentimes a really good idea just to group your real terms and to group your imaginary terms. Really thinking of complex numbers in terms of what's real, what's imaginary is a good way to organize your thoughts. And then just simplifying this further, we have 4i times a plus n minus 656. So because of this I, our real and imaginary part actually ends up being switched. So our imaginary part right now is 4 times a plus n, and our real part is negative 656. So if you remember that strategy yesterday that we called comparing parts, or in other words here, comparing coefficients, what we do is we say that two complex numbers are equal only when the real part is equal and the imaginary part is equal. So we used the analogy yesterday of dealing with the plane, right? So 2 points are equal only when the x coordinates and y coordinates are equal. So same type of idea here. So on this side, we see that the real part is a, and on this side, the real part is negative 656. So that's how we know that a is equal to negative 656. And then we do the same thing with the imaginary terms. So we equate the imaginary part. So we have 164i is the imaginary part here. And then the imaginary part on this side is 4i times a plus n. So we equate those two here. And then we just simplify this a little bit because we know what a is. We know it's negative 656. So now that we have this equation for n, we can just solve for n. So it's just a very basic, just some algebra, isolate n, and what you should get is 697. All right, so just quickly going to check the Q&A in chat for any questions here, and if not, we'll go to our second and last homework problem.
Someone's asking, are we using complex numbers today? No, this will basically be starting scratch from game theory. A lot of it is, it's really a lot of it's just logic. So don't worry if you didn't understand yesterday, but today is completely different.
Yeah. All right, so then I will move on to the last homework problem. So the points 0, 0, a comma 11, and b comma 37 are the vertices of an equilateral triangle, and you want to find a and b. So at first sight, you know, if this wasn't on a complex number slides presentation, you know, it almost seems like it goes into geometry, right? So what this is getting at, and you know, you actually could put in a geometry presentation, but this gets at sort of the second half of what we talked about yesterday, which is sort of the geometric way of understanding complex numbers. So because complex numbers are not only useful algebraically, they have meaning geometrically. So if you remember some of the properties we talked about, like multiplying by I being a rotation by 90 degrees, or the fact that when you multiply two complex numbers, their magnitudes multiply and their angles add. So those two key concepts really can help you solve a lot of geometry problems. So the hint, if you read it, was that the triangle. The goal is to put the triangle in the complex plane. So that's the strategy here. So the problem kind of makes it seem like you just put on your normal coordinate plane, but it actually can help you to imagine it that it's on the complex plane, which is actually quite a common strategy. So if you put them on the complex plane, then b plus 37i is a rotation of 60 degrees of a plus 11 about the origin. So that sounds a little fancy, but I'll just draw a little picture to help you visualize it. So we can draw our coordinates here. So this would be the real axis, and this would be the imaginary axis. And then we have our 1 point at the origin here. So that's 0, 0. Let's say a comma 11 is over there. So in other words, a plus 11i. that's a plus 11i. And then we can say, let's say that b plus 37i is around here. So b plus 37i. All right. So because we know it's an equilateral triangle, we can just draw this in here. So because we know it's an equilateral triangle, we know that this angle is 60, right? Because that's equilateral triangles, angles are 60. So this sort of might sound weird to you, the statement, the point b plus 37i is a rotation of 60 degrees. So basically what I was just trying to say here is that if you take a plus 11i, rotate it by 60 degrees, what you get is b plus 37i. So we can actually say that a plus 11i times cis 60, so if you remember that's cos 60 plus I sine 60, that's equal to b plus 37i. Because if you take a complex number and you multiply it by cis 60, the magnitude of cis 60 is just 1, so the magnitude doesn't change. But its angle is 60, so it'll add an angle of 60 to a plus 11i. So if you take something and then add 60 to it, angle-wise, you're just rotating it 60 degrees, and that's exactly what we said b plus 37i is. So we know that this is equal to b plus 37i, and then what you see here in parentheses is just what cis 60 is in rectangular coordinates, just because we're dealing with a's and b's here, so rectangular coordinates will be a little bit more useful to us. And then we go back to our strategy that's very useful, as you can see. It's equating the real and imaginary parts, right? So here, this is the real part. This might be a little confusing because typically we call b the imaginary part, but just recall that here b is actually the real part of our second number. So b is the real part here. A over 2 minus 11 root 3 over 2 is our real part. So if you just do out this multiplication in what I'm highlighting right now, you'll get that the real part is this. And then likewise logic for the imaginary part. So you get 37 is your imaginary part because of this 37 here. And then again, do this multiplication, and what you should get is this. And then you have a system of equations with 2 variables and 2 equations. And we've solved equations like this before, so we don't write all the calculations, but hopefully when you work out the numbers, you should get that a is 21 root 3 and b is 5 root 3. So multiplying the 2 together, you should get 315. All right. So definitely a harder problem, but I think it really encompasses what we tried to cover yesterday, which is both the algebra of complex numbers as well as their geometric properties. Yeah, we got some people putting in the answer in the chat. Nice.
Great.
All right, so if there are no questions, Foyez will let you get to game theory.
Get to game theory. Okay, great. Okay, so today we'll be talking about game theory, and I apologize if there's noise in the background. It's raining here in New York, so I apologize if there's any noise. But yeah, so today we're talking about combinatorial game theory, and I'll explain what all of this means as we go along. So game theory, like what is it? So game theory is exactly what it sounds like. It's essentially just the study of games. And so a couple of examples are chomp, nim, chicken, rock, paper, scissors, tic-tac-toe, chess, any game that you can really think of. And game theory really gives us a lot of like terrific techniques to really analyze these games and understand, you know, how people win, what are some strategies going into it, and what are really the properties of this game. And so it also has like a lot of applications. So like, why would we study games? So a lot of games are not exactly like games that we always play. Games are sometimes represent you know, interactions between multiple players, where they're interacting in some sort of format, and that's why this application is so useful. And game theory allows us to analyze these things mathematically. And so a couple of applications, I think the biggest one I would say is economics. That's really what we see, where we see game theory come up the most, just because I know a lot of game theory is done, research is done by economics professors. Yeah, and so in the chat, we're getting some questions about the last slide, like nim, chomp, chicken. Yeah, there's a lot of games that in game theory that many of you may not have heard about. I definitely did not know about a lot of these games before, but tune in to this lecture and maybe the next if you're really, really interested, and you'll learn what all of these are. Um, Game theory is also really important in military tactics. Really understanding like the strategy of how should like a military move forward, or what tactics should they take. And so game theory really informs us a lot about strategy. Of course, in marketing, behavioral economics, very similar to economics, politics, especially in something called voting theory, a lot of game theory comes into play. Evolutionary biology, and this is might be surprising to a lot of you, but game theory also comes into play in evolutionary biology, and it's maybe not like how we define like it wouldn't be like maybe perhaps like a competitive game where there are two defined players, but nature comes into play, and we're essentially what we're doing when we apply game theory to evolutionary biology is we sometimes try and find like stable evolutionary states. So we call those, I believe, stable evolutionary states. And so that really tells us, you know, what sort of things are stable. And so game theory can really help in that analysis. And finally, sports. I think this is really cool. Just of course, strategy in any sport. That's probably prolonged. Just like whether you should hit in tennis, like which shot should you hit? Should you hit a cross court shot? Should you hit a down the line shot? Should you hit a drop shot? Should you come to the net? Or in football, what play should you run? Should you throw? Should you run? Should you if you scored a touchdown, should you go for a 1-point or 2-point conversion? Things like that. And I actually did. I think there's a really interesting problem that relates to the Orange Bowl a long time ago. I would say sometimes, I think maybe sometime in the 1980s, between the University of Miami and Nebraska, which really delved into this idea of whether you should go into for a 1-point field goal and a 2-point field goal. If you essentially have if you have two chances to do it, and you want to win the game. And so I would suggest you look into that. If you want, you could just look up Orange Bowl game theory, Miami, Nebraska, and a lot of this will definitely show up on quick internet searches. But it's very, very interesting. I actually did a project on that. That's why I know. That's why I really know about it. That one about the Orange Bowl. But yeah, I think it's really, really applicable and important. So let's move on if there are no questions. Okay, great. Okay, so let's talk a little bit about like the history of game theory. So game theory is definitely a relatively new field of applied mathematics and economics. And it was first first introduced in 1944. And really, I would say that's when we would say like game theory is born. In 1944 with the publication of the book Theory of Games and Economic Behavior by John von Neumann, who many recognize as the father of game theory. And so if you think about it, like 1944 is not even 100 years ago. And so that it's really definitely a relatively new branch of mathematics compared to many other existing fields. And so some prominent game theorists include John Nash, who's well known for something called Nash equilibrium. I know I'm spitting a lot of words that maybe you guys don't, you guys may not know about what a Nash equilibrium is, and that's totally okay. I believe we'll be talking about Nash equilibrium in our next lecture, from the 3 to 5 lecture. But essentially he was very prominent in showing that, and that's a really, really important term and I would say tool in game theory. And another prominent game theorist is Lloyd S. Shapley. And he is really, really important. The one algorithm I know that he designed an algorithm, I believe with, that's called the Gale-Shapley algorithm. And it essentially solves a problem called the stable marriage problem, which essentially allows for matching. How can we form a stable matching given like some people's, given two people's preferences? And how do we do that when we expand that over like n people, where we have a group that's choosing and a group who's essentially applying. in the case of like the resident matching program. So it's essentially like if a group who wants to propose something and a group who's doing like the choosing, how can we form like stable matching pairs? And that's really important in the national resident matching program, which, if many of you don't know, that's essentially after you go to medical school, you're matched with a resident program somewhere in the nation. And so essentially all the students coming out from medical school are applying to residencies, and they provide their preferred basically a ranking of residencies they want to go into. And residents, I believe residencies like where they're held also choose applicants, and this algorithm that he uses is very, very important and comes into play in the national resident matching program. So I think that's really interesting to see like real life application of where these sort of like game theoretic algorithms come into play. So yeah, let's move on. There are no questions. So what is a game? So a game is formally defined as having the following components. We have a list of players, a list of possible actions or strategies that each player can choose from, outcomes, and payoffs for each outcome. So I believe the first three are rather explanatory. You have a list of players, people who are playing the game, strategies or actions they can take. So essentially, what can they do in the game? Outcomes, essentially who will win and what will happen. But payoffs is maybe not exactly too explanatory. So I would, payoffs are essentially just values that we associate with each outcome. So essentially like a higher value sometimes will mean, usually will mean, oh, this is a better outcome. And so payoffs really serve as the way of ranking outcomes and preferences. And they're really important in identifying how we choose strategies. And so there's two types of payoffs. There's numerical payoffs, which are really useful, and there's essentially ranking preferences. And these are called cardinal and ordinal payoffs. So the numerical and ranking preferences. So, and the ranking preferences really essentially say, oh, which outcomes do I prefer better? And there is a way that in game theory that we actually try and like essentially try and associate numbers with these rankings sometimes if it's not convenient with us. And yeah, the way you do that is a lottery. I won't go into that, but yeah, usually payoffs are just really a value that we associate with each outcome. So these are the 4 parts. For anyone taking notes, I'll make sure there's nothing in the chat and Q&As to give you a second to copy down if you need. Yeah, let's move on. Okay, so there are a couple of assumptions that we do make, and so in game theory, as we study, and these assumptions are very, very important. So the first assumption is that we say that all players are rational. And the second assumption is that players have common knowledge. And so what do these terms even mean? So I think most of you have seen at least have an idea of what rational means. But we define this in game theory in a very specific way. So players who are rational, we say that players want to maximize their payoffs, so the values that come with their outcomes. Players are able to rank their outcomes properly. So they're able to choose really like some sort of preferences over outcomes, saying which one do they want more than the other. And we say that players can do the necessary calculations to determine the best outcome. So that essentially, in some ways, you can think about it as like they'll always do what's in the best interest for them, right? And they can calculate, if one strategy is better than the other and which one to play or which action to take. And so those are the 3 assumptions we make when we say all players are rational. And then definition of common knowledge. I think this is one that maybe many people don't know about. And there definitely is a specific definition. So we say that there is common knowledge in the game if every player that's playing the game knows all the components. So strategies, payoffs of each outcome, if they know who else is playing it, all the other players, and outcomes, and if they know all the outcomes. Essentially, but the one key thing for common knowledge is that something that's really important for common knowledge is just making sure that everyone knows it. But on top of that, everyone needs to know that all the other players know it. So this might be a little confusing. So if that's confusing, definitely just let us know in the chat or the Q&A. But yeah, so the idea is like that for each player, they know everything about the game, and they know that everyone else knows the same thing. And so that's really important for common knowledge. And so yeah, so the idea is that these players are essentially playing optimally, as someone noted in the chat. Yeah, so yeah, there's a lot of games. I would say like almost all of the games you play like have something to do with game theory and can be analyzed with game theory. Even like someone mentioned Monopoly, I definitely do think that could be represented in some game theoretic way with probabilities and chances. For some of you who know Ticket to Ride, that's a board game. It has a really interesting game theoretic and graph theoretic approach to analyzing those strategies. So yeah, a lot of these games that we play, board games, all those sorts of things can definitely be applied. So yeah, let's move on to the next slide. And so what is combinatorial game theory? So in the beginning of this presentation, I mentioned we were going to talk about combinatorial game theory. And so how is this any different from game theory? So game theory usually just deals with, you know, a game played between any amount of players. And I'll explain as we go down, as I go through this definition, what how they might be different. So a combinatorial game is one that is a sequential game, meaning player one can go first, and it's a sequential two-player game. So that's very important. So there's two players and it's sequential. That means so player one will go take a move, and then after player one takes a move, player two will take a move, and then player one will take a move, and player two will take a move, and so forth. And this is different than like I guess like general traditional game theory, because traditional game theory can also include simultaneous games, meaning that both players make their decision of what strategy they're going to use or what action they're going to make at the same time. So good example, rock paper scissors. That both players are essentially choosing which move they're going to take at the same time, rock paper or scissors. Yeah, and then so a combinatorial game also has something called perfect information. So everything is known about the game by all players, meaning no elements are hitting, meaning that one player, there's not like a certain outcome that one player is not sure of, or there's a strategy that one player doesn't know he actually has, or a move that he doesn't know he actually has, or he doesn't know, or there's no player that doesn't know what payoffs are associated with outcomes. Essentially, she'll be able to, she'll know each player will know all of the necessary components of the game. But notice it doesn't necessarily imply common knowledge, meaning that the players don't know that every other player knows. They don't necessarily need to know that every other player knows all the components of the game. And finally, it's deterministic. So that means there's no like randomization mechanism. And so what's important here is you can think about, yeah, Monopoly is a good example too. With Monopoly, you roll a dice to see how many spaces you're going to move. And so in that sense, there's a randomization mechanism. Just because you know you're rolling dice, and so you don't know how many moves you're going to make. So that kind of serves as like the chance factor, and the chance factor comes into play a lot with game theory. Yeah, when you deal with a ton of different games, deal with a chance factor. And so that is not the case in combinatorial games. Each essentially, the game is essentially the game is essentially played like with all the players knowing what's happening. They know what possible outcomes are happening, what possible moves are possible, and there's no really like randomization to that dictates their moves. They can choose whichever one they take. So is rock paper scissors deterministic? Yeah, I mean, yes, because you're choosing essentially between all three of these options. And so essentially there's nothing stopping you from picking rock. There's nothing stopping you from picking scissors or paper or things like that. And so that's why I would say it's deterministic. Someone asked, is tic-tac-toe a combinatorial game? I believe so. It definitely fits. Yeah, I think so. It fits this definition. Someone asked, is the game theory course that Maya and I took open to all high schoolers? So unfortunately, this course was offered by our school, by Trinity, to us, and I think it was just an amazing opportunity. We took it with a group of students, just a couple students that came from a couple schools in New York City, and we came together every Tuesday and worked on game theory. And so, yeah, I don't. It's not like an online course or anything. It's a course offered by our school. Yeah. So there are a couple more questions. Do computers use game theory to play chess, for instance? Yeah, this is a terrific example of applications for game theory. So computers are definitely used to implement game theory. And a great example that we'll talk about in the next lecture is something called prisoner's dilemma. And there was I can explain it later, but essentially there was a tournament where people were dealing with a prisoner's dilemma situation. And there was where each person had to develop a machine or program that would play other people's programs. And they wanted to see who would essentially have the highest total payoffs at the end. So that stay tuned for that in the next lecture. Okay, let us move on. Will Trinity be offering it next year, and how would one sign up? If you're a Trinity student, you could definitely email me about this, but I'm not sure. With the case of coronavirus, everything is changing, so I'm not exactly sure. So let's move on. Okay, so an important principle in game theory is something called is something called a symmetry strategy or a copycat principle, and the idea of this strategy is just to copy the exact move of the other player in some format. So really, you want the other player's move to essentially to inform the move you're going to make. And so that's the idea of it. And it may be a little complicated to understand now. But when we get into strategies and we start talking about problems, this will all become very clear. And so you should note that there's a more complicated version of this symmetry strategy copycat principle and the repeated prisoner's dilemma, which we'll talk about in the grades 5 through 8 lecture, but I thought I'd mention it. And it's a strategy called tit for tat, where essentially we cooperate on the first move and mimic exactly what the other player does on the previous turn. And this idea essentially promotes, cooperation usually. And so that's actually I was talking about this tournament that happened, I think, back in 1980. The winning strategy that someone programmed was using tit for tat, and it was only 4 lines of code. And so that's really impressive, just because everyone else was everyone else is using since everyone else was creating like 100, 200, 1,000 line codes, it was really interesting to see that 4-line code would win it all. And so, yeah, let's get into our first combinatorial game. And so we say that we're going to play this game that's called chomp. And so what is the definition of chomp and how do you even play it? So we say that, we'll say that Foyez and Maia are playing the game chomp. Maia goes first and Foyez goes second. And each player takes turn choosing a block on the board and removing every block above and to the right of it. And the player who is left to take the bottom left piece, which is the poison block, loses. So the idea is if someone is playing, if one of us chooses this square, we essentially remove all these pieces. So above and to the right and everything all the way over here. So everything comes out above and to the right of it. And so we have this following theorem. Let me just make sure everyone understands the game in the chat. Sorry, because
Chat and Q&A looks good.
okay. So yeah, I hope you guys understand this game because it'll be important that you understand how we're playing it. And so we have the following theorem about chomp. So we say that for any m by n board, so any really rectangular grid that we're playing on, the first player will always win if they play rationally. Or in other terms, they choose the most optimal strategy at each turn. Sorry, that should say turn, not term. And so, so I would say, I actually think like you guys should maybe try and play the game yourself. Perhaps if you have a piece of paper, draw a grid and think about what pieces you can move. Or if you have like tiny pieces, if you'd like to essentially like take a couple small tiny ripped pieces of paper and put them in a grid-like format and try to play it yourself and try and convince yourself, you know, that a first player can win. And then we'll really go about proving this. And I definitely love to see if you guys can think about this proof. And I'll give you a hint in a couple minutes. But I definitely love to see if you guys can play it. And so yeah, that's really interesting. And this idea, when I'm talking about the first player will always win if they play rationally, we say that in the game of chomp, it's a first player advantage game. So meaning the first player will always when we say a first player will always win, that means if they play optimally, so they'll definitely have the advantage because they're usually always going to win if they play the right moves. So I will go back to the definition so you guys can learn, like, just make sure if you can set it up. But yeah. So what if the board is 1 by 1? Well, we usually consider the case where the board has at least one more piece than the poison square. Can you take more than one block at a time? So yeah, technically, so essentially look in this, essentially look at this picture here, and look at this scenario. So let's say this is Maia is taking a move. So she's the first player and she's taking the move. So she essentially chooses to take this block here where my cursor is. So in this move, she's gonna remove this block, this block, this block, this block, because she's removing every block above and to the right. So that essentially includes like everything in this region, in this whole region that may continue. So that's the whole idea. Yeah, I see some good things in the chat. Yeah, I see some really good things in the chat. But remember, like a complete proof doesn't tell me like a complete proof doesn't necessarily need to tell me the winning strategy. And I can tell you right now, in an m by n rectangular board, where m and n are two different numbers, greater than 1, there's actually we can say that player 1 wins, but we actually don't know what the winning strategy is, and no one has ever proved like what the actual winning strategy is, and how each player would go about this. But you'll see as we get on, there's specific cases where we know exactly how to win. And so that I think is really cool. But for the general case of like n by n rectangular boards, we do not know how to win in general. Like what we don't know exactly what the winning strategy is and essentially how to move in each scenario. But we do know that the first player will always win if he plays optimally. And I guess I'll just make a comment on essentially some people might ask like, how would you even analyze this sort of game? Or essentially, how would you analyze what strategies work? And so a powerful method in game theory is called a game tree. And I don't think I'll get into it today, or we'll get into it this lecture, but if you have any questions, definitely just email us. And you can do your own Google search. Game trees are very, very useful in trying to determine this sort of trying to determine what strategies and are good and who will win. Yeah, so just to clarify, so I hope you guys have this all copied down. We're saying that in any rectangular board, the first player can win if they play rationally. And I'll give you a hint. The idea of the proof is using something called strategy ceiling. And so you want to suppose that the first player takes the top rightmost piece. So I hope you guys are playing it. So it takes the top rightmost piece. And you can show something about what player if player 2 takes it, takes some piece, then player 1 could have just taken that piece in general. And so try and arrive at, I'll give you another additional hint, try and use a contradiction. Yeah, and we'll go over this problem very soon. Actually, I'll let you guys play this. If you want, we can take a break. If you guys have any questions you want to ask us in general, whether it applies to game theory, or again, like yesterday, we basically just answered questions about anything in general. Whether it's about us, about Trinity Math Team, I don't know, about New York City, whatever you want, like whatever you really want to, anything you really want to know about that you think or game theory or anything we talked about in the past, we'd be happy to answer it. Someone's asking, would it be possible to apply this to Uno? Yeah, I mean, Uno is a game, but I do think that there definitely is a randomization mechanism, which is like the cards you pick up, right? And the order of the cards in the deck. So that depends on how you shuffle it. So I don't think it would be a combinatorial game, but it definitely is a game, and it'd be very, very complicated to analyze. I think just because the way I think about it, the game tree would be very, very large. But yeah, I would definitely do a Google search. I'm positive, like game theory, there's definitely game theoretic approaches to Uno. Yeah, so we're on a break. We'll come back around maybe like, since we do have a lot of material to get through, 2:07 maybe, 2:08, something like that. But we'll definitely get started around sometime like that. Oh, good question. When playing chomp, can the poison block be placed anywhere? I think that's it. I think people have worked with that sort of variation, but I actually don't think that's possible because you'd have to redefine your moves. I don't think actually, no, I don't think I've ever seen that in that sort of variation. You'd have to redefine the moves because if it was anything other than the bottom left piece, when you take all the pieces above and to the right of above and to the right, if it if the piece if the poison piece is not in the middle, then you'd essentially be taking the poison piece with you. And so you could just essentially you would just cut off whatever like is to the left and below the poison piece when analyzing that game. So no, I've never seen it in that sort of format. We will not be talking about the card game cheat today. Someone asked, how would game theory apply to sports? Because sports depends on how well you perform in the game. That is true. But the idea is if you're playing optimally, there's of course chance of all involved and things like that. And that's where we introduce probabilities into game theory. So there's a lot of moving components, but if we try and like simplify a game, like I know in football games, there's always someone all the way at the top in the boxes watching and really just trying to analyze the game to see which one is the best move, which one is the best play to run next, because we're assuming the players will perform sometimes. And so the idea is, at least in football, it's really about like what play you should run next. And perhaps you can include like, a player's stats within there to include like probabilities on how well they'll perform at executing this play. And so it's definitely a lot of moving parts. But yeah, that's in the case of football. I guess in the case of tennis, it's like you're about to hit a shot. Which shot should you hit next? Right? So should you hit a cross court forehand? Should you go inside out? Should you hit it down the line or things like that? How did you guys prepare for competition like math counts and AMC? Did you do anything specific? Yeah, I mean, I would say all of us here, we participated in math counts and AMC when we were in middle school and AMC. I did not go to Trinity. I entered Trinity in 9th grade, so I went to a different middle school. And so we definitely had meetings and we did some practice, AMC. Really, I would be mostly concerned. I was really just more interested in just learning a lot of mathematics in general. The competitions were just fun ways to solve problems and things like that. But I really just enjoyed learning mathematics. I don't know. What about you, Akash? Do you have any input?
Yeah. So I think I'm in a similar boat in terms of where my interests lie, but there are certainly a lot of people who really like the competitions. So, if prepping for that is your goal, I guess the biggest piece of advice would be is a lot of practice, really. Taking past tests, there's a finite number of those, but you'll be shocked to find the number of so-called like mock tests I get. People make a fair amount of those. So if you're really interested in AMC scores and things of that sort, practice would definitely be the best way. Just you'll learn topics along the way, which is definitely cool. And then just, I guess, also making sure that you really, really do understand the solutions, because if you understand those very well, it'll definitely help you when you see problems similar to it. A lot of problem solving skill comes down to exposure in a way. Sometimes some things will just come to you because you're like, oh, I've seen something like this before. So the more things you see, the more likely you're to be your reaction will be, oh, I've seen something like this before.
Yeah, I see a lot of people are talking about like even and odd number of squares. I think this is just a little weird to think about because there's so many orientations that you can have in chomp that even and odd, like they do account for all the cases, but it's just very hard to analyze in that sort of sense. So I would definitely approach this by contradiction and using the hints. I do not know of any online courses available to take by high schoolers on game theory. I'm not. Yeah, I don't. But yeah, if you're interested, there's definitely like maybe do some quick Google searches. You can definitely email us, ask us questions. Yeah.
Also getting some questions about if there will be another camp either next year or sometime soon. So we're not 100% sure about that yet, but we are considering posting more content after this camp is over. So, you know, in August or during the school year, so sometime soon perhaps. So, you know, if that's something that does end up materializing, then, you know, definitely be sure to be on our YouTube page, subscribe to see anything else we post. I think there definitely seems to be a lot of interest in game theory, at least in these presentations. So if we do publish some more stuff, we can definitely, you know, follow up on these sort of intros to these fields. Is this the last day? Yeah. So for this camp, this is the last day. We have another session at 3 p.m. that's also on game theory and a little bit different. So if you want, definitely tune into that. But for the time being, this is our last session. But as I said before, the YouTube channel is probably the best way to, I guess, you know, stay in touch in a way. Yeah, so definitely subscribe there. We might be posting some more stuff there. Yeah, I think that's the best way to see what we're up to.
Okay, since we do have a lot of material, we're going to be talking about one more game on top of this, and we'll do actually a problem that showed up on the AMC this year that had to do with game theory. So let's just get started and dive right in. So this was an exercise. Yeah, I said try playing the game on paper and seeing what you would think. So hopefully you guys all did that. So let's just start with the formal proof. So we proceed with proof by contradiction. So let's remember what that is. We assume we assume something that is the opposite of what we want to show, and we show that by that assumption it leads us to something that is not true, which means that our initial assumption, which is the opposite of what we want, is not true. So what we want is true. So we say that suppose the second player has a winning strategy. And so notice that just the key realization is, I guess we'll get to it actually in the next couple slides. But so we'll suppose that the second player has a winning strategy. So let's say the first player will take the top rightmost piece. So he takes. Okay, maybe I should explain this first. So suppose that when we say suppose that the second player has a winning strategy, we always say that either the first player will have a winning strategy or the second player will have a winning strategy, because both of them can't win. We have to have a winner and we have to have a loser in this game. So the person that wins and the person that loses, and so only one of them will have a winning strategy. And so we'll show that we'll suppose that the second player has a winning strategy, and we'll show later that it's the first player actually. So the first player will take this top rightmost square here, that's shaded gray. And so, so what does that do? It just removes this piece because there's no pieces to the above and to the right of it. So now we deal with this position. And so now let's say the second player will pick square S, which is colored dark gray. So she'll pick anything here. Player two will pick, let's say, suppose this square S, this gray square S, and it will remove every single piece above and to the right of it. So all these shaded squares are removed. So this move, remember, is part of player two's winning strategy. And so now we have to notice that player one is left with the following scenario. So this is player one taking a second move. And this position is part of leaving player one with this scenario as part of player two's winning strategy. But you should notice that player one could have given player two this same scenario by just choosing by just choosing this square to begin with, right, and removing all of it, right? And player 2 would have to essentially deal with this scenario. And so player 2, in some sense, player 1 is stealing the winning strategy of player 2. So if player 1 takes can take this move, can make this move, we say that player 1 has a winning strategy because he can put player 2 in this scenario. But notice that we said that a player has to either have, only one of the players can have a winning strategy. So if player 2 and player 1 has a winning strategy, that gives us a contradiction. Because we assume that player 2 was the one with the winning strategy. But now you see that if player 1 just chooses this square here and removes all of it, oh, sorry. And he removes, and player 1 removes all of it, player 1 is going to be have that winning strategy. So that's a contradiction. So our initial assumption that player 2 has the winning strategy and is always going to win is false. And so thus player 1 has to win. And he will, and player 1 will always win. Great. Yeah, great. Let's move on if there's no questions. Okay, great. So let's say we play chomp with a square board instead. So this is one of the cases we can actually find a winning strategy. And so the problem I challenge you guys with is to find a winning strategy for the first player of chomp if the board wasn't in n, if the board was in n by n squared. And so I think this is really important. And I'll provide you a hint in like 2 minutes. Yeah. Okay, I can give you guys a hint. So here's the hint. Oh, sorry. So we want, so the hint is to use what we called before as the copycat principle or symmetry strategy. So try and implement, you know, some sort of symmetry and mimicry in your solution. So yeah, I'll give another 2 or 3 minutes. Yeah, for you guys to solve this. And in this case, some of you are trying to put in into n, trying to analyze it separately in even and odd cases when n is even and odd. And while that is a good strategy sometimes for some problems to really break it up into some cases, in this case, I can tell you that it doesn't matter whether n is even or odd. So that's actually a quite interesting piece, because a lot of people would think to really split this into even and odd, because that deals with that changes the number of pieces you're dealing with, and maybe you can make some sort of divisibility or number theoretic argument. But really the idea here is that it doesn't matter whether it's even or odd. Really the argument is the same. Just a couple more minutes. All right, let's go over it. Okay, so the way we're going to approach it, of course, I give the hint of the copycat principle or symmetry strategy. So we'll say that we'll let a sub ij denote the piece in the ith row and the jth column. So like a sub 1, 2 is the piece in the first row and the second column. And this is just for our ease in using it. So we say that the first player will first choose piece A22 and remove all pieces above and to the right of it. So the first player she'll pick this this piece right next to the poison square, so one diagonal away. And next, the second player, they'll choose some other piece that's either on the horizontal or vertical axis. So let's say the second player, they choose this dark gray piece, and so they'll remove every piece above it and to the right, and so they'll remove all this. And what the first player will want to do, they'll essentially copy exactly what the second player does, except on the opposite axis. So across this, so basically they do the exact same move except across this dashed line. So they'll remove these two pieces. And notice that if you keep doing this, we're essentially creating the same scenario that for the second player. And the second player essentially at some point they'll have to take this piece, and the first player will take this piece right here, or vice versa, and they'll always be left with a poison square. And the idea is, if the second player has a move to make, that's not taking the poison piece, the first player also has that move. And so we're essentially allowing ourselves to always have a viable move, and that will leave the second player with the poison piece. And so the second player will lose, and the first player will win. How are the homework problems going to work for today? Unfortunately, we're not going to have homework problems since today is the last day. But if you have any questions, definitely just email us. And yeah, so let's move on to the next problem. So what are some bad first moves? And so the idea is there any move the first player shouldn't make? Yeah, in an M by N board. And it doesn't necessarily have to be a square board. But is there any move they shouldn't make in an M by N board at least? Or is it, yeah. Okay. Many people are saying is picking the poison square a viable move? No, that would be a terrible move, a terrible move. But yeah. See, a couple more minutes. Let me just see to make sure. So we'll just say in this case that the poison square is not a move that the first player wants to take. Okay, just a couple more. Okay, great. I'm seeing some great responses. So, okay. So let's say, so we'll talk about a couple pieces, first moves that the player shouldn't make. So the first player, noticed that they shouldn't choose any square on the bottom row, right? And why is this the case? If the first player chooses a piece on the bottom row, essentially we're left with another M by N scenario, an M by N board. And so the second player has to take, essentially is dealing with an M by N board. But remember, we showed in the first scenario, in the first theorem, that when dealing with an M by N board, the first player will always win. So in some sense, like if the first player takes, if the first player plays rationally, so if the first player takes a bottom, one of these bottom squares, the second player essentially becomes the first player, because it can just be like we restarted the game. We're starting with another M by N board, but now the first play, now the second player becomes essentially has that advantage now, because they're dealing with an M by N board, and that we said was first player advantage. So that's definitely a terrible move to make. So don't make that move. And if the so that's one of them. Yeah, if the board is not square, some of you said it, I did not include it here. If the board is a rectangle and not a square, they shouldn't take this diagonal piece that we labeled in the square piece. Why? Because essentially the second player can now leave, the second player can leave the first player in this L-shaped format, this symmetrical L-shaped format. And that gives the second player the advantage to win. So that is not a good move. Usually, I would say the best move to take, usually the move to take is to take the first piece over here, but after some analysis, it's definitely not clear how you should approach the game in a general M by N scenario. Okay, so let's talk about the case where we have a 2 by N board, so 2 rows and N columns. Can you find a winning strategy for chomp played on a 2 by N board? If so, prove that it works. If not, prove that it doesn't exist. So I'll give you 2 minutes for that, just because we are running low on time. And there is a whole another game that we will talk about. So I'll give you guys until 2:30. And I'll give you guys a hint. There actually is a winning strategy. And a good way to think about this is like in the same way, what sort of scenario do we want to give to the second player, or the first player? What sort of scenario, if we have the winning strategy, do we want to give? Do we want the other player to face when we're playing them? Another hint. Many of you are asking if the first player should take the block diagonal to the poison block, and I would respond to that as a no, and perhaps you can think about why that is, like as the first move. Think about the square case, and how the second player can put themselves in an advantageous position. Okay, let's go over it. Okay, so the solution is the first player will always win, and if they play rationally. So what the first player must do is they must choose the top right piece. Now, now we can break it up into the following couple scenarios. We'll break it up into the following couple scenarios. Notice that this was very similar. Taking the top right piece was very similar to how we dealt with it in the m by n case. And so the way we deal with this is, so we say that now after we take this top right piece, the second player can choose, we split the second player's move into the following two cases. They can choose any piece on the bottom row. And if they do that, the player will subsequently choose the top right corner again. So if they choose any piece on the bottom row, they'll remove everything above and to the right. And so they will be left with another 2 by n board, or 2 by n prime board in this case. And the first player will subsequently choose the top right corner again. If the second player chooses a piece on the top row at, let's say 2, q, for q less than n. So they choose it, let's say they choose this piece or this piece or this piece, any other piece on this top row. Then what the first player will choose is a piece at 1, q plus 2. So if sorry, that should say q plus 1. Sorry. So suppose the second player chooses this piece. The first player will choose then this piece on their next move. And the idea is we're leaving them with this sort of like L shape. And at some point, if we continue doing this, we'll essentially run into the position where it's the same as the square, where we are left with only this piece, and this piece. So these 3 pieces, and then you can use mimicry from there. So that is the winning strategy. So I hope that makes sense. I'll check the Q&A. just to check if there are any questions. Okay, very good. So we say note that if the first player chooses anything other than the top right corner first, the first player will lose. Why is this the case? And so the idea is we show that this is a winning move, correct? And so suppose the first player chooses this piece, right? Then the second player can put the first player in this similar L-shaped piece, which we show that there's a winning move for, which we show that's part of the winning strategy, putting the other player in that sort of L-shaped format. And so the advantage now goes to the second player. So that's exactly why we don't want to choose any other piece than the top right corner, because the second player will be able to essentially steal the first player's winning strategy. Okay, and so now the second game we're going to talk about today is NIM. And so what is the definition of NIM? We say that there are n piles or heaps of chips. And so you can think about these as like tokens, chips, beans, whatever it is, just n piles of chips. And that's what we will use. And we say that Foyez and Maia are take turns playing their move, with Maia going first and Foyez going second. And on each turn, a player removes chips from one of these piles. And a player can only remove chips from one pile on each turn, and they must remove at least one chip. And sometimes there will be a limit to the number of chips you can take from a pile, and sometimes there will not. So those are different scenarios we'll take a look at today. And the players who takes the last chip will win. So that's very important. So I hope you guys kind of understand it. I'll make sure there's no questions on, at least the definition of the game. Someone says like Pringle chips. If you'd like to think of it like that, it's essentially just any sort of like n object. You can think of it as n coins and beans. Yeah, I actually attended a lecture that used beans. They passed out like beans, and we played NIM with other people. So that was interesting. But yeah, any sort of like n objects in a pile, or k objects in a pile. So I hope that makes sense. So the first question is, suppose we only have one pile of chips with a positive integer number of chips. And notice that there's no limit here, so that's very important. Who will win, and what is the winning strategy? So I'll just give you guys 1 or 2 minutes. So we're dealing with one pile NIM. I'll go back to the definition so that you guys can just take a look at this, and we'll go over it in a minute.
Once again, just to clarify, you can only take chips from one pile. So I see some people asking, why can't the first player just take all the chips?
Yeah. Okay, so let's just go over the solution. So this is actually a very simple case of NIM. Yeah, the first player always wins because we said there's no limit on the number of chips they can take in this case. First player will win. There's only one pile, they'll take all the chips. And so the idea here, at least in this case, is that there's no limit on the number of chips they can take. And so since there's only one pile, they'll just take all the chips from that one pile. So yeah, this is just like an introductory problem to get you situated with the idea of NIM. But now let's talk about kind of like a restricted one pile NIM. So suppose we have only one pile of chips with a positive integer number of chips. And in this case, suppose each player can take 1, 2, or 3 chips. So who will win, and what is the winning strategy? So I will give you guys, give you all a couple of minutes to solve this problem. Remember, there's a positive integer number of chips. So make sure to you can't just say make sure to consider all cases with any n number of chips in that one pile. Sorry about that. Okay, I'll also give you guys a hint. There are specific scenarios when either player can win, I believe. Yeah. So yeah, think about what scenarios player 1 might win and what scenarios player 2 might win. And I highly, highly advise playing with smaller examples to get the idea of this. So like start playing with 1 chip, 2 chips, 3 chips, 4 chips, all the way up to whatever number of chips you want to play with. And then perhaps that sort of idea will give you, the solutions to those smaller cases will give you some insight into the general solution. And remember, both players can take 1, 2, or 3 chips, and you really don't the first player does not have control over what the second player does. The second player does not really have any control over what the first player does. They pick independently. Okay, let's dive into the solution. Okay, so I claim that if the number of chips in the pile is a multiple of 4, then the second player will always win. And so how does this happen? So whatever number of chips the player 1 chooses, say it's either 1, 2, or 3 chips, player 2 will always choose 4 minus n chips. So if player 1 chooses 1 chip, player 2 will choose 3 chips. If player 1 chooses 2 chips, player 2 will choose 2 chips as well. And if player 1 chooses 3 chips, player 2 will choose 1 chip. And so notice that player 1 will always be dealing with a multiple of 4 as the number of chips. So 4k chips for some integer k. So at some point, you can argue this by induction. The player will face, or something actually called method of descent. That also, you just have to, you essentially show that at some point the player has to deal with 4 chips. And this is true because the player 1 will always face 4 chips, and since the number of chips is decreasing all the time, the player 1 will always face 4k chips, and since the number of chips decreases every single time, player 1 will face 4 chips. And so no matter how many chips player 2 takes at that point, whether it's 1, 2, or 3, player 2 can take the rest and win. But notice that if it's not a multiple of 4, player 1 can essentially take can essentially make player 2 face a multiple of 4K chips. So in that scenario, player 1 will always win. So player 2 wins if the number of chips in the pile is a multiple of 4, and player 1 wins if in any other scenario.
Right. Just to clarify with some brief examples, let's say we start with 17 chips, right? I'm player 1. Using this strategy of multiples of 4, if I just take 1 chip, then suddenly, let's say Foyez is player 2. If he has 16 chips, whatever he takes, the next number I want it to be is 12, right? And then whatever he takes from there, the next number I want it to be is 8, and so on until we reach 4. And then once it's 4 and it's Foyez' turn, whatever he takes, he can't, I will have the ability to take the final 1, 2, or 3 chips.
Exactly.
Right? And if we were starting with 16 chips, and whatever I take, Foyez can keep it at 12, 8, 4.
Exactly.
Really completely dependent on the multiple of 4.
And so for those of you familiar with number theory, this has a lot to do with mods. The idea is you're essentially trying to make, make the other player face a number that it's 0 mod for. And so in some sense, you can map each move to a number that corresponds to something mod 4. And so that's kind of where number theory comes into play. If you don't know about mods, don't worry. The idea is you just want to make, if you're dealing with 4K chips, so if you're player 1, if the number of chips in the pile is a multiple of 4, second player wins. If any other case, player 1 wins, because they'll just take enough chips so that the number of chips in the pile that player 2 has to face on their first turn is a multiple of 4. And so now let's go to this idea of when we have 2 piles of chips, each with the same number of chips, and we say that there may or may not be a restriction on the number of chips we can take. But for our purposes, let's assume that each player can choose either 1, 2, or 3 chips from one pile during each move. Who will win, and what is the winning strategy? I'll give you, since we do have a couple more problems to get through, I will give you guys just a couple minutes. Sorry. Just about 2 minutes. So yeah. Yeah, and in about a minute or two, I'll give you a hint. Sorry if this is a little rushed. We do have a lot of material to get through, and we're just running a little low on time. Okay, so the hint is think about using a symmetry strategy. Yeah, think about using a symmetry strategy. Perhaps something like how we used in chomp. I'll just give you guys another minute or so, see what we're getting in the chat in the Q&A. remember in this case that the number of piles, number of chips in each pile is equal. Looks like a lot of you are getting it. Okay, great. Let's go over. So the solution, as many of you noted, player 2 always wins because in this case, we have the same number of chips in each pile. So essentially, like I said, we're using a symmetry strategy, and many of you have mentioned this as well. Player 2 will essentially copy exactly what player 1 does. So if player 1 takes X chips, X number of chips from pile 1, then player 2 will take X chips from pile 2. Sorry, there's a little bit of typo there. And so player 2 will always be able to take the last chip because if player 1 can take some chips from the pile, there will always be chips left in the other pile. And the idea is if player 1 has a move, player 2 always has a move, right? And so at some point, when player 1 takes all the chips, the last chip in one of the piles, there will still be some chips left in the other pile, exactly the number that player 1 took on their last move, and so player 2 will just take the rest of those chips. So I hope that makes sense. So let's move on to this next problem. We're talking about 2-pile nim again. So suppose we have 2 piles of chips again, but this time let's suppose there's a different number of chips. And so we suppose there's no restriction. We can say that there's no restriction on how many chips each player can take. But for our purposes, let's assume that each player can choose either 1, 2, or 3 chips from one pile in each move. Who will win and what is the winning strategy? Sorry, here I think there's another typo here. I think I said first that there's no restriction. Yeah, there should be no restriction. So this is not true, I believe. This definitely does make it a little bit more complicated. So this part is not true. Sorry about that. If you guys already have the solution, perhaps you think about what happens if I impose this restriction. I don't think we'll talk about it here, but it definitely is a little bit more of a complicated scenario. Again, I believe this is a very similar idea from last time. So I'll give about 1 or 2 minutes to go through this. So someone's asking if we'll get to go over chicken. Chicken, we don't have that planned for this lecture. We're actually almost done with this lecture, but it is planned for the next lecture. So please check that out if you're interested. You'll definitely there's something definitely for everyone to learn in that. Okay, let's go over it. So player 1 is always going to win. So essentially, just remember here that we said that there's no restriction on how many chips each player can take. So I crossed out this restriction, but there is in this scenario we are considering that they can take an unlimited number of chips, however many they want to take, but only from one pile. So player 1 will always win, and a lot of you mentioned the symmetry strategy is a little bit the same. But the idea is if pile 1 has k chips and pile 2 has n chips for n greater than k, player 1 will choose n minus k chips out of pile 2, and thus even out the piles. And so the scenario becomes exactly identical to the one we talked about in the last slide. And so the idea is now player 1 will mimic every move that player 2 makes, because now there's an even number there's the same number of chips in each pile. So sorry, this should say player 1 will always take the last chip. If you're taking notes, I can fix that. So this is.
Gosh, can you promote Maya?
Sorry if it's getting a little loud with rain in the background. But yeah, I hope that makes sense. Let's check let's check the chat to make sure. Are we gonna have more lectures after today? We essentially decided, I think Akash spoke about this before, today's the last day of TrinMathCamp, but we are considering making more videos for our YouTube channel, but we're not sure yet, and we don't know what the future is gonna look like, and whether we'll be able to hold this in the future, but stay tuned. We'll update you guys soon. Someone's asking, can they get chips from pile 1 and pile 2 in one turn? No, the definition of NIM is that you can only take chips from one pile at a time. Okay. So let's move on.
To the people asking about it being longer, we also have all the 5 to 8 classes up, and some of them are pretty difficult. So if you haven't attended a 5 to 8 class before and want to see it on YouTube.
Yeah, and if you enjoyed today's game theory presentation, I would highly suggest you attend the 5 through 8 lecture, because there will also be more game theory talked about. I would say maybe the beginning of like defining what games are might be the same, but after that, it's all new material. We're talking about different things, and so I hope you guys will join. Now let's talk about this last problem that we're going to do today. Actually, a problem on this year's AMC. It was problem 14. And so it's kind of interesting to see that game theory shows up in some competitions, but I'll read the problem out loud. And since we only have 5 minutes, I can only really give a couple minutes to solve. So we say that Bella and Jen play the following game on the closed interval 0, n, meaning, so that includes 0 and n on the real number line, where n is a fixed integer greater than 4. They take turns playing, with Bella going first. As first turn, Bella chooses any real number in this interval 0, n. Thereafter, the player whose turn it is chooses a real number that is more than 1 unit away from all other numbers previously chosen by either player. A player unable to choose such a number loses. Using the optimal strategy, which player will win? And my hint, since we only have 4 minutes left, try and use symmetry. If one thing you get out of today's lecture is that symmetry is very, very helpful in game theory. Yeah, just another 30 seconds. Okay, let us go over this. Again, many of you may have been thinking about this symmetry strategy, and the hint was to use a symmetry strategy. So the idea is that there's always going to be a first-person advantage. So the first player will always win if they play optimally. And so Bella is always going to win. So what Bella has to do is select the middle number in the range 0, n. So Bella will put a point at n over 2. And note, this is always possible to find. I believe, yes. So they're choosing any real number. So they're gonna put since n is I believe an integer. Yes, n is an integer. Bella will put a point in the middle at n divided by 2, and then whatever point Jen selects within the range, Bella will copy that. So if it's before 2.5, Bella will, if it's like a number k that is less than if Jen chooses a number k that is less than n divided by 2, we'll first calculate that distance, n divided by 2 minus k, the absolute value of that, and then we'll essentially add that to n divided by 2, and we'll essentially be reflecting across n divided by 2 in putting points. And so notice that if Jen has a move, then Bella will always have a move, and when Jen runs out of moves, well, Jen loses. And so the idea is that Bella will always win, and the idea is to use that sort of symmetry strategy where Bella mimics Jen. And so I hope that makes sense. So I can give you an example of this case. So in the range 0, 5, Bella will put a point at 2.5. And now whatever point Jen puts, let's say it's 1.0. If Jen puts a point at 1.0, then Bella will put a point at 4.0, and they'll continue doing that. And so if Jen has a move to put, there will always be an opening on the other side of 2.5. If we reflect, if we think of it as like a reflection, for Bella to put a point. And so when Jen runs out of moves, Jen loses, and so Bella is always going to win. And so that is all we have today for combinatorial game theory. I hope you guys really enjoyed. Thank you for joining us for TrinMathCamp. Remember that all these presentations and the recordings of these webinars and the actual presentations are available on our YouTube channel, on our website. Please check it out. If you have any further questions in the future, please feel free to email us and contact us. We really hope you enjoyed it, and we really appreciate you guys joining us we really appreciate you all joining us for this math camp.
Yeah, thank you to everyone here. This whole thing is not possible without all you guys just loving math and deciding to spend your time with us. So thanks a lot. This has been super fun, and we hope to see you soon.
5 days went by very, very fast, but
definitely.
We're happy you guys. We hope you really all enjoyed it, and we really appreciate your enthusiasm in math. And we wish you all the best in your future mathematical endeavors.
Yeah.
Please,
and if you're in Trinity Middle School, we can't wait for you to meet us soon.
Yeah. Any questions? If you guys have any questions about us or math or anything, please email us at trinmacnyc@gmail.com. We really look forward to any questions you might want to ask or anything you want to talk about. Thank you all.
Okay.